Let's look at another view of the problem. Let's use the same problem just for simplicity. We practiced slicing it up into boxes, and we sliced it up the same way we sliced up area under a curve in Riemann sums when we first learned about integrals. But we're trying to build up our intuition about thinking about ways of slicing stuff up. So let's try, can we think of another way of slicing this up, probably also into boxes, that would hopefully give us the same answer? And it might seem a little silly for now, but it's kind of like doing mental exercises that will pay off later. So we slice it up into boxes vertically. We could also slice it up into boxes horizontally, right? So we could say, I'm going to draw a box whose ends go through the function like that, and then think, what's the area of this box? But now we're asking, these boxes, their heights change based on how high up they are. So before the heights changed based on the x value, but now the heights change based on the y value. So the area of a box would usually be height times width. But let's redefine the height here to be this measurement from here to there. Let's call that the height, and the width we'll call that measurement. So it's the same way of thinking as the other one, where the width was the skinnier part and the height was the part, and all the widths were basically the same left to right, but now we're saying all the widths are going to be the same up and down, and the boxes are going to change their height this way. So what's the width of that box? So let's save some room here. Well, before we called that width dx, so now that we're slicing things the other way, it would make sense to call it dy. And what's the height of the box? Before we said it was x squared minus x cubed, but now the x values depend on what y value you're at. So go ahead and fill this out based on your intuition, and then and pause the video while you do that, and then come back. Okay, let's think about these curves. This is y equals x squared, which we can translate into, if we solve it for x, so that tells us the x coordinate at any particular y value. That would say that x equals square root of y, right? Just take square roots on both sides. And the other curve was y equals x cubed, which turns into x equals cube root of y. We could put a 2 here just to show the parallelism. So then what's the height of that box? It's the rightmost coordinate minus the leftmost, and the rightmost in this region is the x cubed curve, which ends up with this formula. So that would be the cube root of y minus the leftmost, which is the square root of y. So that's the area of any particular box at any particular y value. So the overall, we'd add it all up, and now we're integrating from y equals 0 to y equals 1 of this expression, cube root of y minus square root of y dy. Is that going to be a super easy integral to do? Horrible? Well, it's not that bad. If I rewrite the cube root of y as y to the 1/3 and square root of y as y to the 1/2 dy, then I can use the power rule. So just for practice, go ahead and write that. This section isn't really all about getting the actual answer. It's about setting up the problem, but it's good to get the answer, practice your integration skills, and it's also easier to check a numeric answer. So go ahead and write what that antiderivative is. So hopefully you paused the video and came back. So y to the 1/3, we'd do 1/3 plus 1, which is 4/3. Then we'd say 1 over 4/3 there. 1/2 plus 1 is 3/2, and 1/3/2. And we do all of that from 0 to 1. If you wanted to check this, what could you do? You could type this all in Desmos as capital F of y, and then type this in as lowercase f of y, and then say capital F prime, and hopefully that would overlap that curve. We aren't really interested in the exact shape of these curves like we were when we were doing chapter 5 stuff. We're more interested in the original drawing here, so I'm not going to emphasize plotting those curves and stuff. So let's do one more step here. So we would plug in 1, right? So we'd get 1/4, 1 to the 4/3, minus 1/3/2, 1 to the 3/2, minus what you get when you plug in the 0, 1/4, 0 to the 4/3, minus 1/3/2, 0 to the 3/2. Now, in this case, since this whole last term is 0, it doesn't really matter whether you have the parentheses or brackets there or not. But if we weren't plugging in 0, it would make a big difference. So it's another opportunity to remind ourselves that when you do big F of b minus big F of a, you have to have that big F of a in parentheses if it's more than one term.